2.1, rates of change and limits B. So this part of the section is the algebraic part. When finding limits algebraically, sometimes it's easier just plugging in x, but most of the time we actually have to do something to the equations in order to be able to plug in x. Here are the basics. This is direct substitution. You're just plugging in, plug and chug, plug and chug. Example 1, evaluating basic limits. So number or letter A says the limit as x approaches 2 of 3. If you observe, there is no x to plug anything into. So I can't actually plug in the 2. Therefore, the limit is just 3. It's itself. This is common and way too easy to get wrong. Please don't get it wrong. B, the limit as x approaches -4 of x. Well, this is just plug and chug. So plug in the -4. And that is my limit. C, the limit as x approaches 2 of the quantity 4x squared plus 3. Plug and chug. So let me see, limit 4 times 2 squared plus 3. So 4 times 4 plus 3. And that's 19. All right, next. D. A little more complicated, but you get the drift. This is all just plugging in. These are basic limits. I don't have to do anything special, but simple old algebra. So the cube root of 2, plug in the 3 for the x squared minus 10. So cube root, let's see, 3 cubed, or 3 squared is 9. 9 times 2 is 18. 18 minus 10. So let's see. The cube root of 18 minus 10 is 8. So there is some number somewhere that if I multiply it by itself and then again by itself, I get 8, and that's 2. E, it's a rational function, right? It's a fraction, no big deal. If I plug in 1, will anything bad happen to the denominator? No, we're good. I can plug in. So let's see. I'm going to write it down here. Plug in the 1 squared plus 1 plus 2. And then the bottom part, plug in the 1 plus 1. So let's see. 1 squared, that's 1. So 1 plus 1, that's 2. 2 plus 2, that's 4. 4 on top. And then 1 plus 1, that's 2. I get 4 halves, which is the same as 2. So this is just the basic stuff. Example 2. It says, assume that the limit as x approaches b of f of x equals 7, and the limit as x approaches b of g of x equals -3. Okay, so like I don't have a real number here, but that's okay, because I don't even have actual equations. I just know that the limits are already 7 and -3. This right here is using numerical values. I don't have a real equation. I don't even have a real x value, but I know what the limit already is. And in these examples, I can just use the limits to answer the question. So for A, I have the limit as x approaches b of the f of x equation plus the g of x equation. Well, since I'm finding the limit, all I really need are the limits of these equations. So I'm going to use them to answer the question. I don't really need the actual equation, the real equation. I don't know it anyway. So here I have 7 plus -3. All I'm doing is I'm adding their limits because I'm finding the limits anyway. And that's 4. B. So the limit as x approaches b of 4 times g of x. I don't know what g of x is, but I know what the limit of g of x is. And that is negative 3. And the limit of 4 would be 4. So 4 times negative 3. C, the limit as x approaches b of f of x times g of x. So I know the limit of f of x is 7, and I know the limit of g of x is negative 3. All I have to do is multiply them. Okay, D, the limit as x approaches b of f of x divided by g of x. So I hope that you get the idea. I'm just plugging in the values. I don't really need to know what the equations are. So I have 7 over negative 3, which is negative 7 over 3. And that's that. Example 3 has to do with trigonometry. So on the right side, you can see that I have a little unit circle going because it's helpful to learn how to doodle one, a little quick sketch with the major points that you know or that you can memorize because you have to memorize them anyway. So I'm just going to go ahead and fill it in. And this is what I kind of expect you to be able to fill in right away. But if I look at my problems, I have x approaching 0, I have x approaching pi, and x approaching 0. So I'm going to focus on 0 and pi. I don't have to do extra work if I don't need it. So I'm going to fill out the coordinates for 0. Well, here's 0, and the coordinates for 0 are 1, 0. And I'm going to fill out the coordinates for pi. Here's pi, right? And the coordinates here are negative 1, 0. And I don't really need anything else because I'm only really focusing on 0 and pi anyway. So there's my little unit circle going, and hopefully those values will help me answer the questions. Okay, A, the limit as x approaches 0 of tangent of x. Okay, so tangent. You actually have to use your trigonometric identities. It makes it easier to do this, these kinds of problems, the trig. For example, you should know, and if you don't, we'll have to brush up on it. Tangent is equal to sine x over cosine x. I'll write it up here somewhere. Tangent of x is equal to sine of x, cosine of x. So I can use that to answer A. A little shortcut with the unit circle, and I'm going to write this in also, is that sine is considered to be the y-coordinate, x, or cosine, sorry. Cosine is the x-coordinate. And then whenever I have to find tangent, tangent is actually going to be the y-coordinate divided by the x-coordinate, which is the same as saying the sine of x over cosine of x. Okay, so A. This is going to be, actually now, I'm going to treat this as the limit as x approaches 0 of sine over cosine, or the y-coordinate over the x-coordinate. So at 0, the y-coordinate is 0, the x-coordinate is 1. So that's my limit. 0 divided by 1 is 0. D. So I have the limit as x approaches pi of x times cosine of x. So I'm going to go ahead and plug in pi. Right? So I get pi times the cosine of pi. So I look on my unit circle, and the cosine of pi is the x-coordinate of pi. Well, negative 1 is the x-coordinate of pi. So I have pi times negative 1. And that simplifies to negative pi. All right, next. I'll do it in a different color because it's gonna be really close. C. The limit of as x approaches 0 of sine squared of x. This can be rewritten in a more friendlier way. I like to rewrite squared trig functions like this. I'm going to write sine x, and I'm going to make it squared. They're equivalent. They're the same thing. I think this is friendlier, and it helps for when you're doing derivatives, which we will get to very soon. So, I am looking for the sine of 0 squared. So I go to the 0 degrees or 0 radians. It's right here. And sine is the y-coordinate, so the y-coordinate at 0 is 0. So here I have 0 squared, which is 0. And that's limits with just trig, some little trig. Okay, dividing out. Example 4 involves factoring. If you look at these equations, both of them, a and b, the x value, I can't actually plug those x values in because if I do, I end up with 0 as a denominator. So for example, a, if I plug in -2 here, I get -2 plus 2, which equals 0. And 0 can never be the denominator. We don't divide by 0, so that's a problem. So we're going to have to factor. So I realize that you may have forgotten how to factor, hopefully not. So I'll write down all the steps to the factoring. But we need to know how to factor. So the top quadratic equation is going to be factored into some kind of binomial, and the bottom is going to stay the same. So I need to figure out what I'm going to factor that into. So I'm going to do the work on the side here. So this is A, this is B, and this is C. So A times C, so that's 3 times -2, that's -6. B is 5. So I need two numbers that add up to 5, but when they are multiplied, they give me -6. So I know 2 and 3. Those two numbers definitely add up to 5. But when they are multiplied, I need them to multiply up to -6. So obviously, when I multiply them, they're not going to add up, or sorry, they're not going to equal -6. So those are not my option. So I go back to the drawing board, and let's see, two numbers that multiply up to -6. Well, I do have 1 and 6. They definitely do multiply up to 6. In order for it to be negative, one of them has to be negative. And they have to add up to 5. So if I make the 1 a negative, -1 plus 6 is 5. So these are the numbers I'm going to use. Now, I always have to divide by a. In this case, a is 3. So when I have my binomials, it's not just enough to write x minus 1 and x plus 6. I do actually have to divide by a, and a is 3. This is what I get. If I simplify the one on the right, for example, I get x plus 2. And then the one on the left, I'm not really allowed to leave the 1/3 there. The shortcut would be to just basically take the denominator and plop it in front of the x. But mathematically, you can multiply that whole binomial by 3. So I have 3x minus 1. So that is how you factor, right? Hopefully that was just a refresher. Now that I have my binomials, I can put them into my parentheses up here. So 3x minus 1 and x plus 2. Now, this is called dividing out for a reason. If you notice, on the top I have an x plus 2, and on the bottom I have an x plus 2. And since this is being multiplied, I can actually get rid of both of those x plus 2's because they divide each other out. And then I'm left with the limit. And yes, you do actually have to write it. Again, the limit as x approaches -2 of 3x minus 1. And now this is easier, and I can just go ahead and plug in the negative 2 without having to worry about dividing by 0 or anything like that. So 3 times negative 2 minus 1. So 3 times negative 2 is negative 6. Negative 6 minus 1 is negative 7. Remember, if I'm talking too fast, you can pause, rewind. That's the beauty of videos. All right, B. For B, I'm also going to factor out, but this is a special factoring. This is a difference of squares. And whenever you have a difference of squares, well, that means that both numbers are actually perfect squares, and they're being subtracted. And whenever you have a difference of squares, this is what it's going to factor out to be. You take the square root of the x, basically. You put an x in each one. And then what is the square root of 49? Well, that's 7. And then you're going to add 1 and subtract 1. All right, so on the bottom now, this is still x minus 7. And if you look, oh, voila. Once again, I have something I can divide out, which is the purpose, of course. And when I'm finished, I am left with the limit as x approaches 7 of x plus 7. And now I can just plug in, plug and chug. 7 plus 7, and that be 14. Yay. Okay, rationalizing. Example 5 has to do with the rationalizing technique, and that comes about whenever there is a radical, and a radical is the square root symbol. That's a radical. And that's when this is going to work. Basically, what you're doing is you're getting rid of the radical from the numerator in order to simplify this in a way that you can actually plug in whatever limit you're approaching. In this case, if I plugged in 0, I'd have a problem. So, rationalizing. I'm going to multiply this expression by the conjugate. I almost forgot the name. I'm going to multiply it by the conjugate. So the conjugate is basically the numerator in this problem. Let's see, 2 plus x with a slight change. Instead of 2 plus x minus square root of 2, I'm going to do the square root of 2 plus x plus square root of 2. And then divided by the same number. And this is valid because I'm not actually changing the equation, because the conjugate, which is what this is, if you do the math, actually equals 1. And you can always multiply by 1. 1 doesn't change anything. This version of 1 is special because it'll change the way the equation looks without changing what it equals. Okay, so that's the conjugate, and I have to multiply all of this out now. And the beauty of the conjugate is that when I multiply this by this, I'm basically going to end up with 2 plus x without a square root. So I'm going to write it on the next line because this is a lot of stuff. So the square root of 2 plus x times the square root of 2 plus x leaves me with 2 plus x. Now, the square root of 2 plus x times positive square root of 2, that's just the square root of 2 times the square root of 2 plus x. That's a mouthful. But then I'm going to end up doing a negative square root of 2 times square root of 2 plus x. And when I do that, they end up canceling out. So a shortcut would be to kind of just ignore the fact that the middle stuff happens, because they always cancel each other out because of the fact that this is a conjugate. And I can kind of skip some steps and forget about the middle term and just go straight to negative square root of 2 times positive square root of 2. And so that's a negative 2. Right, because negative square root of 2 times positive square root of 2, I'm going to get negative, and then the square root of 2 times the square root of 2 is just 2. Okay, so that's the top. Now the bottom. I'm trying not to distribute the stuff on the bottom. So there's x, and then here's the other denominator that I should have like multiplied it by, but I'm just going to leave it alone. And usually leaving it alone helps you more than if you were to distribute it out. All right, so this is my new limit now. I'm going to do a little bit of simplifying. For example, the negative 2 and the positive 2, they cancel each other out. So now I have x on top, then I have this x on the bottom, and then I have all this good stuff. And now I look and I'm like, oh, those x's, they cancel each other out, like for sure. So now I have 1 over the square root of 2 plus x plus the square root of 2. And at this point, this is when you want to be like, okay, can I plug in 0? If I do, will it kill anything? And I can plug in 0 because I'm not going to end up with 0 as the denominator. So let me go ahead and plug in 0. So 1 over the square root of 2 plus 0 plus the square root of 2. So let's see. I have, let me lower this a little bit. Oh, that was a lot. So now I have 1 over the square root of 2 plus the square root of 2, which is just 1 over 2 square roots of 2. For all you calculator babies, you probably push that in and get a decimal. Not necessary. This is a good answer. Or you can actually rationalize this fraction because we don't ever really leave radicals in the denominator. And if I rationalize this fraction, I'll end up with the square root of 2 on top and then 4 on the bottom. And I can show you how to do that if you don't know. Probably on the bell ringer. I'll do that. All right, proceeding. Okay, this is to try it. These are examples that I would like you to try on your own from listening to me babble. That's why it says please pause this video now and try working out the next 2 problems on your own. When done, resume watching. So what you're going to do is you're going to try them and I'm going to work them out off of video so you can see the answers, and then I'll go on to the next example. Okay, so here's all the work. Feel free to pause, please, rewind, etc. to look it over. I tried to make it neat. I'm moving on to the next example. Last part of the notes are special trigonometric limits. These are special because they will always be this answer, and it's just easier to be able to recognize it and memorize it than to try to figure it out, because the only way to do it without a calculator is to make a really long table and figure out the limit, and you don't want to do that. So I'm going to draw the graphs of these so you could see them. Of course, you can graph them, but just so that you can see the limits are what they are. So here are the graphs. So for sine of x over x, the limit as it approaches 0 is right here. It's 1. And for 1 minus cosine x over x, the limit as it approaches 0 is 0. Example 6, a limit involving a trig function. So you kind of have to remember a little bit from pre-calc for this. A, the limit as x approaches 0 of tangent x over x. If I plug in the 0, that's a problem. I need to work this out in a way that I won't be dividing by 0. And the first thing that comes to mind, and hopefully eventually you'll get there as well, is tangent. I know tangent is sine over cosine. So I'm going to use that. So this is going to become 1 over x, and this 1 over x is this right here. I'm removing it from the tangent. Like, they don't have to be written in a fraction together. They can be side by side. And now that I've done that, okay, so limit as x approaches 0 of 1 over x times, and I said tangent is equivalent to sine of x over cosine of x. And then if I use my special trig functions, the ones from the other slide, sine of x divided by x equals 1. So if I can rewrite this in a way that those are together, I can actually simplify this. So let's see, proceeding. The limit, yes, you do have to write this every time you make a new line. So now I have sine of x over x times cosine is still in the bottom, and we'll just have a 1 up there. Okay, so now I can actually do the limit. Sine of x over x, according to my special trig, is equal to 1. And then 1 over cosine of x, I'm going to go ahead and plug in the 0 to that. And I'm going to have 1 over the cosine of 0. And if you want to use the little unit circle from the front of the notes, at 0, the x-coordinate is 1. So 1 times 1. And that's my answer, which is 1. Okay, I'm going to go to C because B is like lower on this slide. I hope you understand. So I'm going to do C. The limit as x approaches 0 of sine 4x divided by x. Now that kind of looks like the special trig limit, but it's not exact because of this 4 right. So I got to do something to accommodate for that. Well, in math, we're allowed to multiply by the number 1 because the number 1 doesn't change anything. But in this case, I feel that when I multiply by the number 1, it's going to look like this. It's going to look like 4 times 4. Because, or sorry, 4 divided by 4. Because 4 over 4 is 1. And the reason I chose 4 is because of this 4. It's kind of inconveniently there, so I need to do something to make the bottom, the denominator, look like this value right here. So I'm going to make the denominator look like 4x. And the only way to do that is to multiply it by 4. But I can't do that just to the bottom, so I'm going to do it to the top also. Okay, so when I actually multiply the stuff out, I end up with 4 sine of 4x over 4x. Now, these two are the same. And since they're the same, I can use my trig, my special trig limit. So, this is going to equal, this whole thing is going to equal 1. And then times 4. So the limit is 4. The shortcut would have been to just look at the number in front of x and be like, oh, the limit is 4. But you have to know why, and this is why. All right, B. So I have the limit as t approaches 0, okay, t, x, whatever, same thing, of sine 3t divided by 2t. So I need to do something to this to make it work for me so that it's actually kind of like the special trig limit. I see that the 3 and the 2, they're obviously not the same number. So I need to make the bottom the same as the top. And in order to do that, I might have to actually not get rid of, but move some stuff around. So this is how this is going to go. I'm going to take this 2, and I'm just going to kind of like remove it from there and bring it out to the front. And since the 2 is in the bottom, it's actually a 1/2. So I have 1/2 times the sine of 3t over t. So now my goal is to somehow make this and this look the same. And okay, the 1/2 is still on the outside, but that's okay. It's a number. It could stay there for now. So B is kind of like C. I need to use the same technique to make the top and the bottoms look the same. So there's a 3 in front of the T. And so I'm going to multiply this by 1, but a special 1, right? So let's see, the limit as T approaches 0. And then I have 1/2. And I'm going to multiply by the number 1, but it's going to look like 3 over 3. And then sine of 3t over t. All right, so I'm going to keep going. So the limit, da 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 da. Okay, so the whole point of multiplying by 3 over 3 is so that I can make this 3 come here. So I have 1/2 times 3 over 1 now, because I kind of moved that 3 from the bottom, times the sine of 3t over t. All right, so there's my special trig function, or my special limit. That should equal 1. So I can do my thing. 1/2 times 3 over 1 is 3/2. And then the special limit should equal 1. So my answer is 3/2. D. The limit as x approaches 0 of sine of x over 5x. Now this one is different because the top is okay, but the bottom is what has this extra number that's inconvenient. But because it's in the bottom, it's actually easier. So I am going to rewrite this with my mathematical powers as 1 over 5. I'm basically like ditching the 5 and making it get out, times sine of x over x. And voila! I have reached the point that I wanted very quickly. This is my special trig limit, sine of x over x. It equals 1. So 1 over 5 times 1. 1 over 5 is my limit. And boys and girls, that is it. I'm sorry if my voice is annoying, but yeah, do your homework. Let's see. Oh, my bad. Please do as many problems as you possibly can on your own, and whatever you can't, bring to class so I can help you with it. Alrighty.